Hello students, we're going to pick up with 9.3 graphing rational functions. And in fact, the topic of 9.3 is really just a continuation of the topic that we started in 9.2, which was graphing simple rational functions. Now they're going to make it just a little bit more complex. And you can see what we're talking about as we proceed. But to start, let's just review real quick what you've learned in chapter 9.2, section 9.2. All right, so this is from this top bubble here is from page 541 at the very top of the page. It says all rational functions of this form y equals a over x minus h plus k have graphs that are hyperbolas. Remember, hyperbolas have a couple branches, and they split off. Okay, so that's a hyperbola. Is the graph, okay, and you notice that it's going to have, it's two symmetrical parts called branches, right? And they have vertical and horizontal asymptotes. So in this case, they have asymptotes, a vertical one at x equals h. Why is that? Well, because we want to prevent the denominator from becoming 0. And you'll see that your graph approaches very closely to the y-axis, which is, well, not the y-axis. It depends on what h is, I guess. If x is equal to 0, it's the y-axis. But x equals h, it's going to approach very closely to that, but not touch it. And it's going to split off and then, graph on the other side of it as well. And then you also have a horizontal asymptote at y equals k. Well, why is that? Well, as x gets really, really, really big, what's going to happen to this overall number? Well, it gets really, really, really small. So then y is going to equal to 0 plus k. Is what your line's going to approach. So the horizontal asymptote then ends up being y equals k. All right, now, that was for this form of function. Okay, so now, and then it says and then you're going to draw the graph. You plot a couple of points on each side of the vertical asymptote, and then you draw the two branches of the hyperbola that approach the asymptotes and pass through the plotted points. So these asymptotes kind of give you neighborhoods. So once you get the asymptotes put in place, then you can find a few points to the left of the vertical, a few points to the right of the vertical, and then graph the rest of the rest of the rational function. All right, now if you have a rational function that's in this form, okay, now how is this different than this above form? Well, this one right here just has a constant here on top. This has a variable in the numerator and a variable in the denominator, and notice they're both to the first degree. They're both linear functions in the numerator and the denominator, as a matter of fact. So that has a few other little things going on. Now, first of all, to find the vertical asymptote, that's going to be whatever causes that to become 0. So if I have cx plus d in the denominator and I set it to 0, what is x going to equal? Well, I'm going to subtract d, right? Subtract d, and I get cx equals minus d, and then I divide both sides by c. And so therefore, I have a vertical asymptote at the opposite of d over c. Because if I were to put that in here, it would cause the denominator to become 0, and I don't want that to happen because then my function would be undefined. So we have a vertical asymptote at that. So whatever causes the denominator to become 0, that's where you're going to have a vertical asymptote. Then in addition to that, the horizontal asymptote, well, let's think about what happens as x gets really, really big. Well, as x gets really, really big, I mean, the fact that I have an x on the top and the bottom, I mean, these become less consequential as x goes off to infinity. And of course, they kind of cancel each other out. So that means that produces a horizontal asymptote at the leading coefficients, a over c. So y equals a over c. So anyway, so I think it's important to kind of have a good sense of how the horizontal and vertical asymptotes, why they come into being, and on these simpler functions that you did in 9.2, and keep that in mind as we proceed into 9.3. All right, so now we're picking up with 9.3, after reviewing a few of the key concepts from 9.2. And this green box right here is your friend. This helps you graph any rational function. So you should keep this page open when you're graphing because it's going to help you immensely. All right, so in lesson 9.2, they said you learned how to graph rational functions of this form. F of x, that's your rational function. It's made up of a function p of x divided by q of x. All right, and in which case p of x and q of x are linear polynomials. Okay, so that's what you did in 9.2, and of course they said q of x, the function can't equal 0 because it's in the denominator. In this lesson, we're going to learn how to graph rational functions for which p of x and q of x are higher degree polynomials. And this green box tells you how to graph anything. Okay, so let's just read over it, and then we're going to use this to graph all the rest of the stuff. So it says, let p of x and q of x be polynomials with no common factors other than 1. So in other words, if you've got a polynomial up here and a polynomial down here, and you're able to factor it out and they have any common factors, before you start graphing, you want to simplify your function, your rational function, before you start trying to do that. And that's what they're talking there. They're basically saying that the top polynomial relative to the bottom polynomial, the numerator relative to the denominator, they're relatively prime. In other words, they have no common factors other than 1. It's already been simplified. Okay, so once you know that's for sure, then it says that this rational function has the following characteristics. The x-intercepts of the graph of f are the real zeros of p of x. Now, why is that? P of x is in the numerator. So this polynomial that's up here, the real zeros of it are the zeros of the function, in other words, are what cause the function to become equal to 0. So if the numerator ends up equaling 0, what's going to happen to my overall rational function? It's going to equal 0, right? So, and that's where x equals, where the function ends up equaling 0, where f of x equals 0, those are my x-intercepts, right? So what they're saying then is if you can find the zeros of the numerator, the zeros of the function, that will be, those zeros will in fact be your x-intercepts of the graph. Okay, so that's where you're crossing the x-axis. All right, now, number 2, the graph of f, okay, f of x, okay, so that's the rational function, has vertical asymptotes at the real 0 of q of x. All right, so again, since q of x, that's in the denominator, again, because I don't want q of x to equal 0, because then my rational function would be undefined, I need to restrict my domain from those solutions, the x values that would cause my denominator to equal to 0. So therefore, I know that I'm going to have vertical asymptotes at the real zeros of q of x. All right, so, and then number 3, this has to do with the horizontal asymptotes. And in section 9.2, you were looking at these in terms of them being like, either two linear functions, or you had a constant in the numerator and a linear function in the denominator. Well, now we're going to be looking at all the different possibilities. So and they look at them in terms of the leading term, the degree of the leading term. So m, just notice that's the degree of the numerator polynomials, and n is the degree of the denominator terms. All right, so in other words, they're saying if the degree in the numerator, the highest degree in the numerator is less than the highest degree in the denominator, if m is less than n, then you're going to be, your graph is what we call bottom heavy. And if it's bottom heavy, your horizontal asymptote is y equals 0. Now, why is that? Well, because the polynomial is bottom heavy, that means as x goes off to infinity, this number is the value in the denominator is going to get much larger than the value in the numerator. And what does that do to the overall value of the rational function? Well, that means it approaches 0. The bigger the denominator gets, the overall number then gets very small. And so therefore we have a horizontal asymptote that's approaching 0, y equals 0. All right, the second possibility is if the degrees are equal, and that was what we did in the section 9.2. The degrees were equal. The second kind of example that they gave you, you had a linear function in the numerator and linear function in the denominator. Well, what happens then? If the degrees are equal, if these guys' degrees are equal, whatever happens back here just doesn't really matter so much because these are going to be the biggest numbers and they kind of cancel each other out. And when they do that, then the horizontal asymptote then becomes the ratio of the leading coefficients. So A over B is what it's going to be. So that's when the degrees are equal. Okay, and then the last scenario is that your graph is actually top heavy. In other words, the degree in the numerator, the highest degree in the numerator, is bigger than the degree in the denominator. And when that happens, it says that there is no horizontal asymptote. And then they said the graph's end behavior is the same as the graph of, okay, so the end behavior, remember how we did end behavior of polynomials, and I can't remember which chapter that was now. Is it 6? So they're saying that if you want to figure out the end behavior, you are just going to divide out the two leading terms and look at that. And if this is a positive number and this is even, then your ends are going to go up. If that's a negative number, A over B is a negative number, and M minus N is an odd degree, then you're going to have it's going to depend. If it's positive or negative, the leading coefficient here, you're going to have, remember it's going to be down on the left and up on the right. And if it's negative, it'll be up on the left and down on the right. So in other words, I don't know, this is like, if this is positive, okay, we'll say it's greater than 0, and this is odd, right? It's going to do this, right? And then if this is less than 0, remember it's going to be up on the left and down. Am I doing this the opposite way? Oh no. Okay, so if it's positive, oh my gosh, I'm getting this messed up.